So for this problem, it says 1.3.1, prove proposition 1.3.4b, which is the proposition. I'll just read the entire thing here. Let xd be a metric space, let y be a subset of x, and let E be a subset of y. For A, E is relatively open with respect to y if and only if E is equal to V intersecting with y for some set V contained in X, which is open in X. Part B, E is relatively closed with respect to y if and only if E is equal to K intersecting with y for some set K in X, which is closed in X. So for part A, let xd be a metric space, y be a subset of x, and E be a subset of y. Let E be relatively open in y, which implies that E is open in yd. Basically implies that the boundary points of E is intersected with E is equal to empty set, and such that E is equal to the interior of E unioned with just the boundary points that are in E, and basically we know that since this is equal to empty set, that this has to equal to empty set, which is equal to the interior of E, and thus E is open here in this relatively open set right here. Therefore, for all x in E, there exists R of x greater than 0 such that the ball y d x for some R of x is contained in E. So for V, let's just let V equal to every corresponding ball right here with a corresponding point in E. And since we proved that the open ball is an open set, and we proved that the union of collection of open sets is open, thus V is open. And so now, with our open set V, we want to show E is equal to V intersected with Y. So let Y be in V intersected with Y. Since Y is in V, this implies that there exists some X in E such that this Y is in this ball. Remember, since this is a collection of a union of balls here. Since Y is in big Y, Y is also in this ball intersected with Y, which is just equal to the ball in the submetric space of Y, which is contained in the ball without the submetric space because since Y is contained in X, which is a subset of E, because remember, E is the collection of all of these things, and thus Y is in E. Therefore, V intersected with Y is contained in E. So now let Y be in E. Since Y is in E, this implies that Y is also in the ball. It corresponds to this YR, which is a subset of the ball that's equal to V right here. So then thus this Y value is also an element of V, and since E is a subset of Y, this implies that Y is in big Y, and thus Y is in this ball intersected with Y, which is contained in V intersected with Y, and therefore E is a subset of V intersecting with Y. Now for the reverse direction, let xd be a metric space, y be a subset of x, E be a subset of y, E equal to the V intersecting with y such that V is open. Let x be in the set E in the y metric space. We want to show that x in the interior of E is in the interior of E in the y metric space. Since x is in E in the y metric space, this is a subset of E, which implies that x is in V. Note that I'm just writing this. These two are equal because E is already contained in Y, but I'm just writing this here just for visualization. X is in V. Since V is open in X, this implies that there exists some R of X greater than 0 such that there's a ball x comma rx contained in, that is a subset of V that contains this element right here, x right here, right here. Since E is equal to V intersecting with Y, this implies that the ball of xd from x comma rx intersecting with Y is also contained in E. Thus, x is in this set right here, which is just going to be the ball in the Y metric space or Y submetric space, and thus I showed that every point in this is in the ball as well, and so thus x is in the interior of E in the Y submetric space. So for part B, let XD be a metric space, Y be a subset of X, and E be a subset of Y. Let E be relatively closed in Y, which implies E is closed in YD, which implies that the boundary points of E is contained in E. And so let's let K equal to the adherence points of XD, which is just equal to this. And we proved previously that the adherence points of any set or of E is closed. And we want to show that K is equal to the intersection of Y, which is equal to E in respect to the submetric space of Y. K intersected with Y is equal to the adherence points of E in the metric space XD intersected with Y as carried on, which is just equal to the adherence points of E in the submetric space Y comma D. And we proved previously E is closed. Keep that in mind. We know that E is relatively closed in Y, and it's closed in Y. That this implies that the adherence points of E is equal to E itself, and therefore K intersected with Y is equal to E intersects the submetric space of Y comma D. So for B in the reverse direction, let XD be a metric space, Y be a subset of X, E be a subset of Y. Let E equal to K intersect Y such that K is closed. Since E is contained in Y, this basically implies that E is equal to E in the submetric space of Y. And we want to show that the boundary points of E is contained in E. Since K is closed, this basically implies that K is equal to the adherence points of K. And we can basically convert this out as such. E is equal to K intersection of Y, which since K is equal to the adherence points of K, I'm substituting it here. And since we know the adherence points is just all the points here, it's just going to equal to the interior of K and the boundary points of K intersected with Y. And as I'm just like kind of wrapping this around to here and here, I can basically now say that E is equal to the interior of K intersected to the submetric space of Y and the boundary points of K in the submetric space of Y as well. And so taking this set as well, since E is equal to this, I can substitute this into here. I'm looking for the boundary points of, there's a small typo right here. This should say the boundary points right here, partial right here. And I know for the boundary points of this right here. And as you can clearly see, the interior of this can have no boundary points, right? Because it's interior. But for this one, it's just the boundary points itself. And so it will just equal to this as well, which is contained in K. Intersected with Y, which is just equal to E intersected the submetric space of Y, which is what I wanted to prove.